Welcome to this evening's TI Technology webinar hosted by Texas Instruments, where we will take a look at how TI-Nspire technology can help your students make connections with transformational geometry. I see that many of you are joining us for the first time, so I'd like to offer a special welcome if this is your first T-Cube Professional Development webinar. We'd also like to thank everyone for completing the live survey on the right side of your screen. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough-to-teach, tough-to-learn concepts accessible to all students. I'm very happy to introduce our two panelists tonight, Dan Ilaria and Steve West. Dan is a T-Cube national instructor and professor of mathematics education at Westchester University of PA. Previously, Dan taught middle and high school mathematics, as well as been a supervisor of mathematics for several school districts in New Jersey. Currently, he uses TI technology with pre-service and in-service teachers as a part of pedagogy classes at both the undergraduate and graduate level. Thanks for being with us, Dan.
Thanks, Mike. Glad to be here.
And Steve earned his BS in mathematics at the SUNY at Oswego, a MAT in mathematics from Rutgers University, and a PhD in mathematics and education from the University of Texas at Austin. After receiving his PhD, he moved to the State University of New York at SUNY Geneseo. During his nearly 30 years at Geneseo, he taught graduate and undergraduate mathematics courses, mathematics methods, coordinated their highly successful secondary mathematics certification program, and served as department chair. So it's no surprise that Steve was also recently inducted into the New York's Mathematics Educators Hall of Fame. Thanks for joining us, Steve.
Thanks, Mike. Glad to be here.
This session is being recorded, and as a reminder, we'll provide a link to the event certificate of attendance at the conclusion of this webinar. Once the recording is available, if you'd like to follow along with your handheld or your software, and we really do hope you will, we recommend doing this with the recording so that you can download the activities, and then pause and rewind the recording as necessary. We don't expect you'll have any audio issues tonight, but in the event that you do, try selecting Communicate in the WebEx menu, choose Audio Broadcast, then click Join. At this point, Dan is going to discuss our agenda.
Thanks, Mike. Good evening, everybody. After we finish our introductions and beginning stuff, we're going to do a brief review of identifying isometries and talk about some of the questions that we need our students to understand when it comes to isometries. And we'll do that using an activity specifically made for this about exploring isometries. And then after that, we're going to go through an activity about dilations that helps students understand the definition of dilations and similarities, and finish off with some examples of the types of proofs that are expected with students based on changes to standards across the country.
Thanks, Dan. And Steve is going to discuss our expected outcomes.
Glad to have you here, folks, tonight. We're looking to show you how to explore using TI technology to explore transformations so that you can better understand congruence, and so your students can better understand congruence and similarity. In the process, we'll investigate and verify the properties of dilations so that students can develop a deeper understanding of a transformational approach to similarity. We hope to learn how to cultivate students' understanding of similarity in terms of similarity transformations. And finally, at the end, we'll show you a way to stay in touch with social media and upcoming events.
Thanks, Steve. Dan, it's all yours.
Okay. So Steve is actually going to start you off by talking about some properties of isometries. So I'll let him start with this page, and when he's ready, he'll let me know, and we'll switch over to the Nspire software and get started on some activities.
Dan, are you going to show that exploring the calculator with the
Or you want to look now?
Yeah, you're going to show them both. We were going to show both of them.
Sure. Okay, everybody. So I'm going to switch over to share my desktop. So the screen that we were just on has minimized, and if you're new to this, there will be a green button at the top of your screen. You can bring that down and open up the chat window and participant window so that you can still follow along with the chat and be able to answer questions that Steve and I are going to ask you throughout the night. So right now, everybody should be seeing two screens. One is my TI-Nspire teacher software, and they should see two triangles. And the other one is a Word document with some questions and a table about isometries. So hopefully that's in view. You've had a chance to open up the chat window, and we'll let Steve run with it.
And if I could just jump in really quickly, because we've had a lot of use in the chat window already, which is great. I just want to make one comment. Whenever you send a chat, if you could send to all participants, which should be at the very bottom of your choices of who to send to, that goes to me and Steve and Dan and everyone, as opposed to just a smaller group. So if you could send to all participants, we'd appreciate it. Thanks.
Well, folks, we're really pleased to have you here tonight. To open, what we'd like to do is to bring back to mind some of the things that we talked about in a webinar last April about isometries or rigid motions, and just as a matter of review. And if I'm not mistaken, that particular webinar was recorded, and the materials should be available if it's something you'd like to go back and look at. But we're going to begin by assuming that we have a fairly comfortable level with the notion of rigid motion. Just a couple of things. I don't have it on the screen, but I'd like to remind everyone what the definition of a transformation is. It's very simple. A transformation is a one-to-one mapping or function from points in the plane onto points in the plane. Very simple. Simply means that every point in the plane has an image, and every point in the plane is the image of at least one thing. What goes along with that is that every rigid motion is uniquely determined by three non-collinear points and their images. That's very useful because that basically what that tells us is that if you have a triangle and you have its image, there will be exactly one rigid motion that maps one to the other. And the question becomes, and it's also one of the things that pops up quite frequently in the Common Core standards, all right, if you have two congruent triangles, identify the rigid motion or series of rigid motions that map one to the other. Now, in order to be able to do that, we've got three questions, and those are in the thing in the center of the screen that Dan has shown you. The first question we're going to ask ourselves is the isometry direct or opposite? That's a fairly simple question. We simply need to compare the orientation of an image and its pre-image. So, for example, if we look at the triangles on the left side of your screen, and we pick the blue triangle and we choose its name, keeping in mind that there are a variety of different names for the same triangle. But for right now, let's just say it's triangle ABC. Well, if you move from A to B to C, you move in a clockwise direction, and therefore its orientation is clockwise. However, if you chose the name CBA, you'd move from C to B to A, and the triangle is oriented counterclockwise. So we need to be able to note which type of orientation a triangle has. So let's start with ABC. And we'll say triangle ABC is clockwise, and its image, triangle A prime, B prime, C prime, is clockwise. If the triangle and its image are the same, then we say the isometry is direct. And it doesn't make any difference how we choose the name as long as they both have the same orientation. That's going to be one of the most important questions we ask. Dan, if you change the triangle. No, well, just flip that one, yeah. All right, now if we look at this example just very quickly, triangle ABC is clockwise, but its image, A prime, B prime, C prime, is counterclockwise. This is going to be an opposite isometry, different than the one that we did before. And we're going to ask that question the minute we look at two triangles and their images. Now, the other two questions are really quite simple. We're going to ask ourselves about fixed points, and that simply means is any point the image of itself. That's called a fixed point. And then we're going to look at line segments and their images and determine whether or not they're parallel. And if you look at the chart that's presented in that center thing, we've got a summary of the things that we talked about last spring. A translation is direct and it has no fixed points. And all line segments are parallel to their images, and so forth down there. So if we have that, we can use those questions, ask those questions to specifically identify isometries. All right, so Dan, if you go back to that first triangle. Okay. Let's ask the question. The very first question, we want to identify what particular isometry maps ABC onto A prime, B prime, C prime. So the first question we'll ask, and we'll ask you folks to use the chat window, all right, is this rigid motion or isometry direct or is it opposite? Well, it looks like we pretty much got that one figured out. Now, let me ask this question then. Can you restrict the number of our isometries? Now, do you have an idea what this might be? Without being specific, I think because we have direct and opposite, you'll recognize that we've limited to 2. So it's either a translation or a rotation. All right. What's the second? The second question we would ask, is there any fixed points? And I'm going to ask you that question. Are there any fixed points? Are there any obvious fixed points? Are there any points that are their own images? You could use the chat to answer. Are there any obvious fixed points? As I watch you folks answer the questions through the chats, the great number of answers is no, and some of you have answered that there's 1, but it's either what I see from the thing 1 or none, and I suspect that those of you who answered 1 have already determined what you think this particular isometry is, or this rigid motion is. But I'm going to ask you, let's look at the last question, see if that helps us out a little bit. And the last question says, is the image of a line segment a parallel line segment? And of course, we're always going to ask ourselves, always. So using the chat, is the image of a line segment a parallel line segment? Okay, so based on the answers that I'm seeing, we've decided that it's either a translation or a rotation, and the images of a line, there are no obvious fixed points, but the image of a line segment is, in this particular case, not always parallel to its pre-image. Therefore, which of the two direct isometries do we have? Those are the answers that I like to see. Dan, would you change the picture? No, change it to, well, we could leave it with that. Change it just by moving it. Okay. That looks good to me. Let's ask, what is this guy? This is sort of, I am an isometry. I am a rigid motion. What's my name? What questions should I ask?
Yeah, I think it would be good if people would, instead of naming it, would say, you know, what are their responses to those three questions? So is it direct or opposite? Are there any fixed points? Are the line segments parallel? And so this way, people get used to thinking of those properties and kind of verbalizing them, because we want our students to verbalize them before coming to that conclusion. So they're kind of stepping through that process in preparation for things when we want students to use isometries for proofs. So I'm seeing some good answers in there, like people are saying it's direct, there's no fixed points, yes, they're parallel. So when we can describe all three of those things, then we can make our conclusion that this is a translation, because that's the only isometry that has all three of those properties that we're identifying by answering those questions.
Nice job, folks. Dan, move that triangle again so that we have one point on top of another.
Okay.
Okay, folks, same game. 3 questions. What are your answers, and who am I?
This is what Steve was talking about earlier about, you know, the question about fixed points being obvious is something really important to students, because the original rotation we had did not have any obvious fixed points, but there was one, and people were identifying it as the center of rotation. And here it's more obvious that there is a fixed point, and that's something that we want kids to notice the difference between. It looks like, Steve, we've got some real good students here tonight.
Oh, we really do. Super. Okay. Let's change the triangle again. Let's try another one.
You want to go to green?
Yep. Okay, folks, let's play the game. Answer the questions, and who am I?
Remember, when thinking about the fixed points, do you see anything that's obvious, a fixed point? And hopefully people are starting to realize the nice thing about looking at these properties, particularly just the direct and opposite, I mean, that takes you down to 2 out of 4 possibilities for what the isometry could be. So that's a real important question that we want students to notice. And it makes it important that they understand how to name figures properly, because that will lead to helping them identify isometries, helping them figure out how to use them to prove things congruent or prove objects similar. And then the other two, is there any obvious fixed points? I don't know. If I grabbed this triangle and said, hey, it now looks like this, the answer to that second one becomes very clear, and therefore what isometry it is becomes very clear. But when it's out here, it might be up in the air as to what students would say.
And of course, one of the things that we're looking at here, and this becomes very important because we're heading towards proving congruence theorems using rigid motions or using isometries. And there's two parts to a transformational proof. Part one is identifying which isometry is the one we need, which is exactly what we're doing in this particular activity. The second part, of course, is showing that the rigid motion that you picked does what you claim it did. That takes a little bit more work. Dan, pull slide A down a little bit. Yeah, that's cool. Okay. Play the game one more time. Who am I?
What's going to be interesting here is whether or not glide reflection is something that's taught in the classroom, because is that going to be part of the curriculum? Is it not? If it's not, then as soon as kids see opposite, it's got to be a reflection. Do we need to include glide reflection? What would be, the mathematics behind that for making sure we include glide reflections in our discussion of these isometries? All important things to think about when it comes to building a curriculum and how kids are expected to work with these in a geometry class.
If I can interrupt for 1 second, we had a great question from Matt, and I think this really goes to both of you. The question is, in the classroom, are you wanting students to say that there are no fixed points as it sits at this point?
At this particular point, the fixed point question is a tough one because it's not obvious. We only see 3 points and their images. And in this particular example, none of those points are fixed. That doesn't mean fixed points don't exist. And that's a hard thing for people to get. Basically, what we say is that particular question doesn't give us any more information here in this particular question. But there's other ways. In order to be able to go, I think you said it was Matt. In order to be able to go back to Matt's question, we know that this guy is either a reflection or a glide reflection. All right. Now comes the time to play the game. If it were a reflection, just if it were. All right, what would the line have to be? And that's the kind of question I want the students to ask. Can anybody answer that question? If this were a line reflection, you may have a different opinion, but if this were a line reflection, what would be the line? And we need to be very specific. You folks realize that I'm terrible with wait time, and I'm working awfully hard on this. All right. What do we know would have to happen if it were David had a good comment, and I'd like to come back to that if someone will remind me. And let me finish this one question. If this were a reflection, what would have to happen? Let's say, what would have to happen to point B? Matt also has a good answer there. What would have to happen to point B if this were a reflection? maybe I'm asking a bad question. If we ignore all the rest of the triangles, what would the line of reflection be if B went to B, if mapped to B prime?
So if we just thought of what would we have to do to figure out the line of reflection between B and B prime, right? So so are we looking at equidistant from the line of reflection?
Okay, well, this halfway in between is providing part of the answer.
Mm-hmm. There's some kind of angle measure, right?
Oh, we're starting to see some people that are putting it in there. Dan, why don't we do what's been suggested here, a perpendicular bisector.
So I'll construct a perpendicular bisector between B and B prime.
Okay, now that's the line that would map B to B prime. If this were a reflection, what would that line, what would be the image of A over that line? Would it be A prime? We know that that line works to map B onto B prime. Will it map A onto A prime? And I see lots and lots of no's. Therefore, we know that it's not a reflection using the perpendicular bisector of B, B prime. What if we tried A prime or C, C prime?
When I construct these, they should actually turn out to be exactly the same line if it was a reflection. So am I kind of discovering that by investigation?
Absolutely. All right, so what we've done is we knew it was a reflection or glide reflection, but none of those lines work that would have to work based on our definition of reflection. So that leads me to think that this is not a reflection, which leaves us with one choice, glide reflection. Now back to, and I think it was David made a comment. Said, would we recognize this instead of being a glide reflection, recognize this is the composition of two rigid motions? And the answer is that's probably the way that Common Core would prefer us to do it, because if you'll notice that the glide reflection is the orphan of the Common Core. And therefore, this turns out to be a reflection followed by a translation, and I think if you imagine it, you can almost see. And this goes back to, I think, Matt's comment about the midpoints. If you take the midpoints of A and A prime, B and B prime, and C and C prime, there's one line that will go through all three of those, and that's the line, that turns out to be the line of reflection, which is part of the glide. The glide reflection is an issue, and it's an important rigid motion, but you will probably never use it as part of a proof. Its role is that it completes the group of rigid motions. That set of four rigid motions in composition forms an algebraic structure called a group. Ray asked the question, could you use a curved reflection line? That's a question I've not been asked. A line is a curve a line, and I think that's something we'd have to resolve to be able to do that.
I would say we'd be working on a sphere, then we could probably do that, right?
Yeah, we run into some other issues on the surface of a sphere, so I think we're
sure.
right now we've assumed Euclidean geometry because we've been dealing with that specific parallel. So
yeah. So how about I jump over to definitions of dilations and similarities, since we have a good grasp on this, and we'll stick with staying in the Euclidean before we end up in some other types of geometry and way off topic.
Yeah.
Let me just go ahead.
Well, we could have some really interesting discussions, but I think it's important that we sort of move on, because we'd like to take a look at this new family, and hopefully in the process. And this is a mirror image of what the webinar last spring did, except we're going to do the same thing for dilations and similarities that we did for isometry.
Yeah.
And this activity is downloadable from the website if you have already got it. There's a whole bunch of information there, but it basically tells us that we have a triangle and we have a scale factor. And we're going to do a couple things in an effort to discover the definition of a dilation. Now, we probably already know what a dilation is, but let's see how we can get our students to find it without just walking in and saying, hey, folks, here it is, here's the definition. All right, Dan, I'll turn the page and I'll try to remember what I was going to tell you to do.
Okay. So the first thing I'm going to do is I place this point so that we have our center. And then I'm going to go in and use the transformation menu. So under transformation, we have a dilation.
Dan, are we on page 1.3?
Yep.
Oh, how come I don't see that? My screen not updating?
I'm not sure. Is anyone having issues out there of not being able to see this screen with the triangle?
I'm also on page 1.2, Dan.
Okay.
Can we maybe try having you stop sharing, even though it'll close all those windows? Stop sharing and then possibly reshare?
Yep, sure. I can do that real quick.
So as Dan does this, all of your chat windows are going to close. And as soon as Dan begins sharing his desktop again, you'll find that chat window underneath that green floating toolbar.
I've asked it to share, Mike, and it's
there we go.
There we go.
You got it? Okay, there we go. It was taking a while there. Okay.
There we go.
Good. Back in action.
That's good. So while everybody was looking at the other page, I was having a grand old time starting this dilation without you. So I placed this point for our center, and I went into menu and transformation and selected the dilation tool. And if I want to make sure I'm using this tool correctly, I can go and hover over that icon and it'll give me the directions. So I want to click my object, then my center, and then the value. And I can either click on that or select that. So I'm going to select the triangle. I'm going to select my center. And we have this slider that's been created up here with the number, so that'll be my value. And my image appears. And one of the first things I want to do is label this. So I'm going to use my control menu as I select each point. And I'm going to slide this around a little bit so I could see them a little better. And I'll just quickly label all of these correctly, I hope.
And as Dan is doing that, it seems like a pain to label things, but as you saw, the orientation became a very important question in isometries, and it's going to be an equally as important question in similarity. So the labeling of the triangle, which establishes the one-to-one correspondence, becomes incredibly important.
Okay, so the first thing we want to do when students create this is say, what do you observe? So type in some observations into the chat as I move point P around, and just note some observations, anything that comes to mind, just to get a couple thoughts out there about what happens. So I'm moving P around the plane, and what are some observations that you notice? Okay, first couple of people are saying that.
Corresponding parallel. Yeah.
Parallel, good. Looking like both triangles are the same orientation. Good. Good. Okay, so good. So you can see, if you're looking at the chat window, there are lots of different things that students can talk about just by moving this around and making some observations. And so now, as a teacher, you can go in any direction that you would like. And so one of the things I'm going to do is create line segments. Just create lines that go from A to A prime, B prime and B, C and C prime. And if I extend each one of these, what do you notice about all three of these lines? Okay, so some people are noticing that these all intersected at the point P. If I change my value for my dilation, do we think that's going to affect this conjecture that these lines are always going to intersect at P? I have some other values here. And so, you know, students make a conjecture. We want them to test that, and we want them to look at different examples. And that's the nice thing about the technology is I can change this around very easily, and students can make an observation about whether or not their conjecture holds. So at 2, it works. At 1, my lines disappeared. At 0, they're all in the same place. Even at -1, it works. Okay,
no,
so
we have a good group of students, because it's important. You notice that the premise is, now obviously most of us probably already know what a dilation is, but your students will make the same kind of conjectures. And as I've read through the chats, we've already made a conjecture that a dilation, we didn't know what it was, but a dilation is direct. And a dilation maps line segments onto parallel line segments, the same kind of questions that we asked before. Now we notice that a point, its image, and the center are collinear. Those are all parts of the definition of a dilation. And I've seen in the chat, too, people making some other observations.
Mm-hmm. And so the only question we really haven't answered is whether or not there are any fixed points with this transformation. So what do people think? What, if they're looking at this picture, do they see any fixed points? Whether maybe they're on the screen, maybe they're not on the screen? Because we had that happen before with a rotation. So any suggestions for fixed points? Okay, so good. So we're getting a lot of people saying P, the point of dilation, is the fixed point in the plane. So that's another property. Maybe not as obvious as it is with the other transformations that we talked about before, because it's just that one point and you're using it to create the triangle, but something we definitely want students to think about as part of answering all those questions. So the next thing we'll
let me just one more thing, Dan. Would you do me a favor and put a point in the plane named Q, any place?
Okay.
And label it Q as you do it. Okay. Mm-hmm. Now do the dilation. And the reason I pointed this out is it's important. When you do a dilation on a point, it's the only time you have to do it. It's different when you do the dilation on a point. The program gets confused between what's the center and what's not. So when you do the dilation on a point, you must choose the center first. So dilate Q. Okay, and now move Q around the plane. Move Q to P. Notice what happens. All right, and that's sort of a way to illustrate the notion of that fixed point. Every other point in the plane has an image, but P is its own image. In fact, what you could do, let's do this, Dan, just very quickly. Find the dilation of P. So dilate, use the tool. Pick the center.
Center, click it a second time, click the number
and
2.
what happened?
Yep.
Now, if you were quick enough, close the tool. If you were quick enough, you saw it get big, but point at P now. Notice it says point. Now hit tab, Dan. Point P, there's 2 points there. It's the same point. P and point P are exactly the same point, so it's fixed. That's another way of actually illustrating that. Sorry to interrupt, Dan. We need to move on because we're going to run out of time.
I saw some people mentioning things about length. So I wanted to grab the length tool from the measurement menu and talk about the length from, let's say, point P to A, which would be 4.5, and then from P to A prime, which would be 9. And if I change the value of our dilation center, we can start to look at the relationship between those lengths and start to ask students about, you know, what's going on? What do they notice about the relationship between PA prime in relation to PA? And let me go back to 2 there so we can see everything on the screen. And if students start to realize that the relationship between those numbers has something to do with their dilation value, now we've got all of these questions answered about orientation, about our line segments parallel, this collinearity point. Okay, Janet had asked about k equals -1, so I'll switch that over there real quick. And now we can talk about distance between points, and now ask students to define what a transformation is.
What a dilation.
Yep.
They've got, all the information is there, and of course, if you're not hurrying along, your students are actually going to be able to produce it. And my feeling has always been that if a student discovers the definition themselves, then they own it. It becomes there, as opposed to me telling them what it is. Yeah.
And so I'm just going to move to a clean page. We put this in just so that we have a nice clean page here, because the part of this activity that follows this exploration is specifically going through all of these questions. Is this dilation direct or opposite? Are there any fixed points? Let's measure the segment AB, so from A to B, and then let's measure from A prime to B prime. And let's do a comparison there as well. And so now students are starting to build their kind of, think of it as the next line in that table that we showed you earlier. Add a dilation underneath. I guess you can't call it an isometry. But, you know, answer those questions, maybe add some other things that they notice. So we have this relationship between the lengths of the sides. We can also go in and measure our angles and take a look at, let's say, BAC. That's 61.2, and B prime, A prime, C prime is also 61.2.
Dan, do me a favor. Grab one of the vertices of ABC and change it. What do we notice about those angles?
Yeah, let me move these numbers so people can see them. Yep. Okay, good.
Now, one of the things students might question, if you look at those two values, we know the ratios of those two values are 2 to 1. Someone's going to say, doesn't look 2 to 1 to me. How do we handle that? What's the problem? And I'm starting to see some answers come in from Jeanette and Janet. That's exactly it. It turns out to be a rounding error. This is measurement. It's a rounding error. Now, I don't want Dan to take the time, but you could go in and change the precision on those two measurements. It's one of the attributes, and you could, as David suggested, change the decimal value. And if you expand the number of decimals that it shows, then you'll see that the 1/2 is a very realistic choice. Dan, we need to flip.
So let's take a look at a page here, and we have triangle ABC and its image A prime, B prime, C prime. And we'll ask everybody to type into the chat whether or not A prime, B prime, C prime appears to be similar to ABC. So if you're looking at, does the red triangle appear to be similar to ABC? Okay. So
now let me ask a question.
Okay.
Is triangle A prime, B prime, C prime the image of ABC under a dilation?
So hopefully everybody out there is thinking of those questions that they were naturally asking on the last page to see.
Is the red triangle the image of the blue triangle under a dilation? And I'm seeing lots and lots and lots of no's. Convince me.
Okay.
Tell me why it is.
Good point. Somebody asked me to measure the angle, so I'll do that while we see if people.
Tim said just a dilation. I'm saying just a dilation. Is it a dilation? Yes or no?
That first angle is the same, BAC. Must be something.
Careful about direct or opposite, folks. Read the labels.
I'm reading A prime, B prime, C prime as I go clockwise. If I come to the other triangle, A, B, C, also clockwise. Yeah, so both clockwise. So
it satisfies one of the criteria. It's direct.
So it satisfies that. We've got some angles that are the same. Let's take a look at A, B, A prime, B prime. And let's take a look at another one, B to C, and B prime to C prime. I think that's looking pretty close, right?
Yeah, that looks pretty close. What was one of the other observations that you made about the dilation? Dan, flip back a couple pages to our dilation. Okay, we can go back now. Or you can move P around a little bit just to see if you wanted.
Does this P not move? Maybe that P doesn't move. I couldn't seem to grab it there, but.
You know, Mark made an observation about they don't seem to be parallel, and that seems to be one of the characteristics of our dilation.
Yeah.
I said something about a fixed point. Go back to that picture again. Yeah. Now I'm going to ask Hannah the question: is there no fixed points, or whoever said, is there no fixed points, or maybe we just don't see it?
That goes back to that question of obvious, right?
Back to the question of obvious. Right. Well, I think, because we're going to run out of time, I think it's obviously not a dilation, simply because the line segments are not parallel. But the dilation is the only thing that we have that changes sizes in the way that Dan has demonstrated. Flip the page.
Yeah, but I think it's really good that everybody out there was thinking through all of those properties to be able to really justify whether or not it is. It appears to be, they appear to be similar, but we have these properties for the purpose of being able to justify it and convince by going through all of them. And if one of them isn't satisfied, the one that wasn't satisfied was the corresponding sides are not parallel, then we know it's not similar by dilation, right?
Great call by Leslie before we change the page. All right, this one, and this just illustrates it's the same picture. It's a rotation followed by a dilation about the center of rotation. Now, it's not obvious, and it wasn't obvious from that picture that that's what it was. But it wasn't a dilation, but it's a combination of two. And what we're going to find as we begin the investigations is that this is not a dilation, but this is something called a similarity. And all a similarity is a composition of a rigid motion, the things that we talked about before, and a dilation. And that produces something that we're going to define as being a similarity, and we'll say two triangles are similar if one's the image of the other under a similarity. Just real quick, flip a page there, and we'll see what looks like. A bunch of information we'll talk about. Flip page again.
Okay.
We got triangles here, and our job would be to prove that these two triangles are similar. Okay, which means the first thing we would check would be, is it a dilation? Is the red triangle a dilation on the blue triangle? What do you think? I see we say it's not a dilation. Do you think the two triangles are similar? Super. All right, therefore, if they're similar, it's not a dilation, it's got to be a similarity. All right, can you tell me what the rigid motion is and what the dilation is? What's the first question we'd ask? Way back to the beginning of the webinar.
So we're trying to figure out, should I do a reflection, should I do a rotation, or should I do a translation? And the way we figure that out is starting to look at, is it direct or opposite? Some people are saying opposite, and so that's our justification for it's a reflection.
Okay, Dan, quickly do a reflection on ABC.
I'm going to reflect ABC over BC, so there's my new triangle.
And now it's positioned correctly, and what would be my dilation?
Okay, thanks. People are telling me my center of rotation is B. Good. Love those fixed points, right? Fixed point is really clear here. Or I hope it's clear. I don't know, how easily students would pick that up without more examples than what we played around with and really focusing on that idea. But then again, these proofs are meant to be kind of a continuation of the learning. So B is my center of rotation. What should I be using as my dilation factor? Is there something I need to calculate? Is there a number that I should just know? Okay, proportional sides. So I'm going to need to do some measuring. So give me some directions about what to measure. Measure the length of
I see a couple signals, then BC, well, or BC to BC prime.
Okay, so here's my prime. Okay, so I have those two. I'm going to just type a text box. I'm going to do big over small, and I'm going to calculate.
I think we lost you, Dan.
Oh, you can't hear me?
No, I can hear you, but nothing's happening on your Nspire screen.
Oh, okay. You didn't see the measurements come up?
Nope.
No.
Oh, there we go.
Oh.
But I think Mike's twitching.
Okay. So I can just select these two values to get my dilation factor, which some people, I think I saw in the chat, said it was 3, and then perform that dilation. So we'll just finish this off and let Mike take us home here. So triangle, my reflected one, my center of my dilation, and my dilation factor, and you can see that our big red triangle is highlighted. It's going to flash, and there we go. We have our, what we want students to do is to be able to tell us what type of isometries and what's the dilation and what's our reflection over what's our dilation factor, what's our center of dilation. We want them to give us all that information, and then if that works, we have our proof, right, Steve?
Yep, and then of course we will show that just really quickly because I know Mike's going to have a fit. But
okay.
Are you still
right.
still on the thing? They need to recognize that activity has a whole bunch of those kind of problems that follow. That's good enough.
Yep.